All right, so we've talked about reference angles, and now what we're doing is we're moving into inverses. Right, we've done inverses with linear, logs were inverses of exponential, and so now we're kind of moving into that with some trig. So before we talk about inverse, let's go back to what the input and output of the sine function are. So the input of a sine function, and a cosine by the way, but the input of the sine function is an angle measure. So anything that you put into the sine function has to be an angle measure, and that's always going to be in degrees or it's going to be in radians. And so really the domain, just to hit that too, is going to be all real numbers, because remember we can go around and around our circle clockwise or counterclockwise, it doesn't matter. What we get out of the sine function is that vertical distance above that horizontal diameter, horizontal axis, in radius lengths, right? And so I can either be one radius length above the horizontal axis, or I can be one radius length below. And so my range is from -1 to 1. So if I think about the inverse is just switching the input and output. So the input to my inverse is going to be that vertical distance, right, above the axis, or right if it's negative below the axis. The output is going to be my angle measure. So like if we think about that, that inverse is actually not going to be a function, because I could think about the vertical distance above, like if I'm thinking about my circle. I have a vertical distance over here and a vertical distance over here that are the exact same, but they have two different angle measures, right? So for that one input, just going around my circle once, we have two outputs, let alone if we go around and around and around. So no, the inverse is not a function. If I think about that graphically, right, on my graph here, right, so again, if we think about the inverse, now my input is the vertical distance, right? This vertical distance is happening 1, 2, 3, 4, right, and continuing on and on. So even graphically, we can see for that input, there's several outputs. But here's the deal. We would really like for the inverse to be a function, right? We want to be able to use an inverse function to input a vertical distance and to get an angle measure out. Like that would be so useful. And so what we do to make that inverse a function in math is we actually limit what we say the domain of the sine function. So we say, I know that this sine function has a domain of all real numbers. But in order to make the inverse a function, we are going to limit the domain. For the sine function, they decided to limit it from -π/2, or if we were in degrees, it would be -90 degrees, up to π/2, right, or +90 degrees. And so the reason why we do that, if you think about your circle, right, so if I think about my circle, I'm sorry, I don't remember which way is the correct way for you guys. So if I think about my circle, right, if I go here, I'm one radius length below the axis, all the way up to 0, and then all the way up to one radius length above the axis. As soon as I start to go back, that's where I have those multiple outputs or multiple angles for that same height. And so we're limiting essentially to just like half the circle if we're thinking about it as a circle as opposed to the graph. And so now this inverse is a function. Now the inverse will input the vertical distance and it's going to output the angle, but it's only going to output angles between -90 degrees to +90 degrees, or -π/2 to +π/2. Even if the angle you're looking for is outside of that, or it's outside of those values, the inverse can only output those values. And so what we're going to have to do a lot of times is we're going to have to use the symmetry of the circle and reference angles to help find the correct angles. So yes, the inverse works, but the inverse is kind of limiting. And so we have to be aware of that anytime we use the inverse function. Now at the bottom here, just note that both of these are what we use in order to signify. So this says arc sine of y is equal to theta. We don't use that as much in this class. I think they use it more in calculus. You'll see that notation more. For our class, we tend to use this one more. So this is like the inverse sine of y is equal to theta. So you input your vertical distance into the inverse sine function, and it's going to output that angle measure. So this is my inverse, and so then you can see here on my circle, the inverse sine function only outputs angles between down here and up here. That's all you're going to get in those two quadrants. The domain of this function goes from -1 to 1, right? I can only be one radius length below or one radius length above. And then, oops, sorry. Can I go back? Yep. And then my range is from -π/2 to π/2. All right, if we keep going, so, oops, All right, so then for number 1, it says the inverse sine of 0.25. So first off, you want to think about what the 0.25 represents. So if it's the input to my inverse, that means that we're talking about a vertical distance above the horizontal axis. So we're saying that the vertical distance above the horizontal axis is 0.25 radius lengths, right? So that's going to be somewhere right here, right? I have an angle if I had a terminal right there, and then over here. So from here to here. So this angle going all the way there. So when I put this right here into my into my calculator, it's going to get me, let's say I'm in degree mode. It's going to get me 14.48 degrees. And so again, that makes sense because this is my first angle here. But if I want to think about what that second angle might be, because I might, nope, then I would need to be aware that I can always find the second angle by doing 180 degrees minus the 14.48. And again, what we're doing is we're using reference angles with the symmetry of the circle. Let's take a look at that. Number 2 is actually going to be pretty straightforward. So let's talk about that one real quick. So this says use inverse sine to determine the measure of the angle alpha in radians indicated on the circle. So first I want you to estimate what you think the angle will be. So we know that up here, if I go all the way up here, that angle is about 1.57 radians. So it looks like it's going to be less than that, obviously. So maybe 1.1 radians is an estimate. Right, you just want to get in the ballpark so that way when you get your answer, you know whether your answer makes sense. That's always a good practice. So if I want to use inverse sine, first off, I'm not on my unit circle, so I have to be aware of that. And so I could have put a first line here that's like y equals r times the sine of alpha. But then in order to convert, I'd divide both sides by r. And so that's kind of where we get here. So this 3.57 dividing by 4 is going to convert my length into radius lengths. And so that 0.82 or 8925 is telling me this vertical distance from here to here is about 0.8925 radius lengths, or 89.25% of the length of the radius. So if I input that length into my inverse function, it will get me 1.103 radians. And that's why I expected. Like, ooh, go us. And so we're on the right track. But now let's say for problem 3, I want to find the angle that's given there. Now I'm not in these quadrants either here or here. So when I'm going to do my inverse, I know that I'm not going to get the correct answer. I should expect the correct answer to be, so I know going from here halfway is pi radians, about 3.14. So here, I don't know, 3.5, 3.6, 3.7 radians, somewhere in there. So we know that should be our answer. So then let's go do the work. So again, I'm going to divide by 6 in this case because that's my radius length. So this is going to convert my length into radius lengths, find the inverse sine of that value. And then I get negative 0.6195. So that's telling me that this angle right here is negative 0.6159. I'm sorry. Oh, I transposed one of those two numbers. Sorry. So that distance is the negative 0.61-ish radians, which means if I'm symmetrical, right, or circle symmetrical, so if this distance is the negative 0.61-ish, then over here is going to be 0.61-ish radians, right, the openness of that angle. And so that's what we're going to use to find the answer. So for this one, it's like I'm going pi radians plus I'm going an additional 0.6159 radians. And so I would just add those here, and we're going to get my actual angle. And notice that it's about 3.76, which is somewhere in the ballpark of where I was estimating it. And so that's kind of where we're using the reference angle of this. The size of this angle is the same as the size of this angle here. All right. All of that has been done with the inverse sine function. So, oh no, we can do the same thing with the cosine function. So let's do that. So it says, what is the input and output of the cosine function? What's the domain and range? We are going to run into the same problems with inverse that we do with inverse cosine that we do with inverse sine. So I know here the input to the cosine is angle measured, the output is the horizontal distance. Input for angle is all real numbers. The output is just from -1 to 1 because I can be one radius length to left and to the right of my circle. The inverse, again, wouldn't be a function, but when we restrict the domain, it does become a function. For cosine, we restrict the domain from 0 to pi radians because over there we have our +1 to our -1 in terms of our radius lengths to the left and to the right. And so this is the notation for cosine. So the inverse cosine will input the horizontal distance to the right of the vertical axis, and it will output that angle measure, and that angle measure is always going to be between 0 and 180 degrees or 0 and pi radians. Again, no matter what angle you're looking for, that's what the inverse sine is going to give you. All right, so if we keep going here, so question 4 is similar to the sine one. So the inverse cosine of -0.75, that input is the horizontal distance to the right of the vertical axis in radius length, so it's negative, so we're to the left. So we're going to be over here, either up here on my circle, or I'm going to be down here when I think about making that, smoothing that angle out. So I input the horizontal distance, it's going to output the angle. In this case, if it's in terms of my degrees, let's go with, then my angle that's swept out this way is going to be 138.59 degrees. Let's take a look at a couple examples with cosine. So actually this is the same problem as it was with sine, but now we're going to look at cosine. So cosine is looking at horizontal, so we're going to look at the x-coordinates, right? So we're going to use the 1.8 that's given there. And I'm going to do the exact same idea. So I'm going to take x, I'm going to divide it by r, right, to convert my distance to a radius length. So I do 1.8 divided by 4, right? So that tells me that this horizontal distance from here to here is about 0.45 radius length, so 45% of the length of my radius. When I take the inverse cosine, so when I take that 0.45 and I input that to my inverse, it's going to output my angle measure. Notice that that's actually, I think it was 1.102. That's actually the same angle measure that we got if we use the sine. So when I'm in quadrant 1, it actually doesn't matter whether I choose the x-coordinate or the y-coordinate, because I can just use that to, because both of those inverses will return the correct angle. It will output the correct angle. If I take a look at number 6, so again, this is the same one, but now we're going to use inverse cosine. So I'm going to use that -4.89 value. So -4.89 divided by my radius length, right, is going to get me this, which is my horizontal distance in radius lengths. I'm going to input that to my inverse cosine function, and it's going to get me 2.522. But that's the angle from here to here, which I should expect because cosine is only going to give me angles in the upper half of my circle. So we actually have 2 ways of doing this. Some students like one way, some students like the other. I'm just going to kind of talk you through both. So one is that I could use symmetry. And so if this angle from here to here is 2.522 radians, then this angle from here to here is 2.522 radians. And so I could find the angle I'm looking for, the black one, by essentially doing 2 pi and then subtracting out the 2.522 radians. And I'll get 3.761. So that's one method. That's the way I tend to do it. But some students I've just experienced they're like, I just don't see it. So some of them will do something like this. They'll say that I know from here to here is 2.522 radians. Well, let me find this little reference angle here. So they'll do pi minus 2.522, and they're going to get 0.62 radians. So from here to here, this angle is 0.62. Again, because of symmetry, that means this angle, here, is 0.62 radians, and so they will then do pi plus 0.62 radians. And you'll get the same thing, so it really doesn't matter. I don't care which way you go about solving it, just pick the way that makes the most sense to you, and then always make sure and show me your work, just because that way if something goes wrong in your calculator, I can always follow what you're doing.